Hello, Pete Baum. Hello, Michael Schwartz. Let us do some AMC wonderful stuff today. I am actually quite psyched. I wonder if I can. Oh, I can. I can share screen here, which I am about to do.
Oh.
I want to throw some red meat to our base here, as they say in the political blogosphere, in that what I want to do today is I'm going to throw you straight into the deep end. I'm going to ask you to do the thing that most students try to do when they first start studying for the AMC. And doing it in the beginning is a real error because it'll really dissuade you from pursuing it farther, and it kind of focuses you on some of the wrong things. But in this case, it may turn out to be just the right thing because of the training and framing you've had up to this point. What I'm going to do is I'm going to put up on the screen problem number 25 from the 2010 AMC12B.
Oh, you're starting at the deep end.
Yeah, okay.
And the reason I'm going to do that is I think there's something to learn from watching you orient. Flail and orient around something that is alien to you.
Okay.
And then we'll talk about it afterwards. So let's start there. I'm going to start by sharing screen, I hope. That looks good. You can see that okay?
Yeah.
All right. So let's, we can all watch your faces as you do this. That might be fun. But let me have you just kind of get into it. Let's see what happens.
Mm-hmm. Oh, my goodness.
I'm still reading. You're a faster reader than I am.
Well, you're a faster thinker, so it balances out.
Exactly. And it's not like you're only going to read this 5 times. There's this, you know.
Yeah. Wow.
In a minute, I'll tell you the story of when I first read this problem, but I don't want to spoil your experience with mine just yet.
Of course not.
No.
Wait, what? I was fine when it was POW 144, but okay.
I mean, that look on your face, Pete, says so much, right? It's like you are, by any reasonable measure, a math genius who's been coaching people for the better part of half a century. And I still think that's the right face. It's like they're going to ask, what? What?
Right. They gave me this function. I was like, oh, this Wes guy doesn't know what he's talking about. This is going to be easy. Then I got to the end and not so much.
Yeah.
So do you want us to just try solving on our own or talk our way through it? What are we supposed to do now?
I think I'd like you to take a couple of minutes doing whatever it is you do. And then we'll ask, okay, what did you do during those few minutes? And I think it'll be really interesting to see how the answer compares and contrasts to the common answer, stare and panic. Okay. Let's pause here. We'll get to click the resume button here shortly, but let's pause here.
Sure.
So what I want to hear about is the transition from OMG to whatever it is you're doing now, because clearly both of you have made some transition. I'm not suggesting that both of you are on the path to a solution or that you're entirely comfortable with this or anything of the sort. I'm just saying neither of you have that OMG face on anymore. So clearly something useful has happened. What is it?
So
let's start with you, Pete.
So I need to gather some data because clearly the values are so large such that this is not something I'm going to do by brute force. So weirdly enough, I'm going to start with some brute force using much smaller numbers. I mean, I'm just going to follow, forgetting about the 2010 to the nth. I'm just going to find out what the sum is from 2 to 2, 2 to 3, and I was up to 2 to 12. I was just acquiring some data to see if there was anything that made sense to me from that. So I solved this problem from, instead of being 5,300, I solved it from 2 to 2 up to 2 to 12.
So I hear some implied things there. One of the things that I hear implied is that you know what the question's asking. You understand that it's a very large number of things you need to combine up. And so you're taking the first few items on the list, starting to figure out what they look like in the hopes of either finding a pattern or at least getting some intuitive feel for what the heck is going on here.
That's correct. That's as far as I've gotten because I was still writing them out. But that is exactly
Sure. I wasn't even able to get that far the first time I looked at this problem, but we'll get into that in a minute. First, Michael, let me hear about your experience so far.
Well, the first thing I did is just to express 210 as a product of primes.
2010?
I'm sorry. Yeah. Thank you. Yeah. It was 210 after a second. Yeah.
Probably 201 after a second.
Hopefully one. Yeah.
Sorry.
2 times 5
Okay.
times 3 times 67. Yeah.
Yes, that's what I have. 2 times 3 and 567. Sorry, my words aren't matching my thoughts. Anyway, so and then it occurred to me to do what Pete's describing, and I didn't think it would work because I hope I'm wrong, but we'll wrong with that for a little bit. But I didn't think the pattern would really be discernible, but actually,
to be clear, given that this is using the bit of test logic of this is 25, I didn't expect it to be either. Like we did that problem a couple weeks ago with, the mod 2 problem where do these two lists intersect, and the answer was none, and they didn't intersect. And I was pretty confident on that one that actually the problem seemed easier, so that there would be a pattern I could quickly discern. I actually am operating on an assumption that there is not.
Right.
And yet I'm going to do it anyway because I'm hoping to, as Wes was saying, see something I can glean from it, even not something as direct as, this is mod 1. And it wasn't anything simple, but that there would be something there that would help me bootstrap up to something real.
Yeah. I think bootstrapping is really key, right? I often do that. I'm like, I don't know what I'm doing here. Let me try a thing that I think is closely related to the problem. It's not going to connect to a solution in any way I see right now, but the way I like to put it is, I'm in the middle of a dark room filled with furniture. I'm looking for the exit. Like, if I just stand here, nothing's going to happen. Whereas if I wander around the room and bump my shins a little bit, I'm going to learn something. So I got to start there.
Well,
it does occur to me that you could also you could ask such questions and whether these have any more evident answers is a different question. But you could ask such questions as, can you determine the power of 2 here? Can you determine the power of 3? Can you determine the power of 5?
Sure.
It seems unlikely to be. It seems unlikely that 2. It seems unlikely that 67 is the relevant prime number here. Prime factor.
Okay, let me pull us back a minute because I'd like to take a moment to tell the story of when I first read this problem. So it's this problem was first made as part of an AMC nearly 15 years ago at the time that we're recording this, and some small number of years after it was published, probably a decade ago, I was administering this exam as a practice test for a group of AMC students in a conference room a few towns away. And so here we are. These kids are working mostly on problem 1 to 15. I'm sitting around. I got nothing better to do. I've got to be sitting there. And so I'm reading the test. I'm looking through it, and I come to this problem, and I think, whoa. So I just start reading it. And here's my internal experience as I'm reading it. Okay, for every integer n greater than or equal to 2, let pow of n be, okay, we're going to define some function of n, be the largest power of the largest, wait, what? The largest power of the largest prime. I read that 4 or 5 times, still didn't quite click what it was. That divides n, okay, what is that? For example, oh, thank God, for example.
Yeah.
Pow of 144.
Yeah.
Right. Pow of 144, 12 squared. So 2 times 2 times 3 times 2 times 2 times 3, 2 to the 4, 3 squared. Oh, equals pow, 2 to the 4, 3 squared. Okay, cool. Equals 3 squared. Oh, I see. So the largest prime is 3, and its largest power is 3 squared. Okay, so pow of 144 is 3 squared. In effect, I'm doing what Pete is doing, right? Is just trying to get my footing around what the heck this thing even is. What's the largest integer m such that 210 to the m, oh God, divides, I don't even know what that symbol is. What the heck is that symbol? That's what I'm thinking. I'm like, what is that thing that looks like 2 Roman pillars holding up? What is that? Holding up to 5,300. And that's the moment at which I did the thing that was the beginning of my thinking around the idea of presence, fluency, and boldness. Okay. I'm looked at that and I said, well, I know what Polya, the author of How to Solve It, the master of heuristic, I know what he would say about this. He would say, use wishful thinking. Hope that you can figure out what it means. Because if you can, you'll be right, probably. And if you can't, you weren't going to solve the problem anyway. So go for it. So it's like, well, I don't know what that is, but it looks a little bit like a pie, except it's clearly not a pie. And it's in the place where I expect a capital sigma to be. Because a capital sigma would mean this is a sum. And in a flash, as I'm saying that, it dawns on me. Capital sigma is a sum. I bet capital pi is a product. Could that work? And then I think through the rest of the problem with that idea in mind, and it's like, that would make sense. And that's how I learned what this notation was. Okay. And that's totally available to anyone. You don't need to know this. Yeah, go ahead.
Oh, it's funny because I did that without even realizing I was doing it. I was like, it's not a summation. If it's a summation, this problem's completely hopeless anyway. There's clearly no way this problem is solvable if that's a summation sign. So I'm just going to assume it's multiplication.
Yeah.
Like literally that's, I was like, I don't know what it is. I didn't even get through Greek letters. I don't know my Greek letters, to be honest. And I was like, well, it's multiplication because I want it to be multiplication.
Yeah. And if I'm wrong, screw it. There's nothing I can do about this anyway. Right. And that's such a, like that, it's a flash of insight, but it's a flash that's primed by thinking the right kind of framing thoughts. And I think it gets skipped over constantly by students, by coaches, by competitors. And it's so important. It's like, okay, I need this to be a product for this to make sense. Okay, I've made an assumption. I'm going to be aware that it's an assumption, but I don't need to put a lot of attention on it because it's not like I'm going to make a different choice later if it turns out to be wrong. Like, this is all I got.
Right. Well, and when I'm speaking to my students, I always, because I have these, we've talked about my struggling skills list, and this is one of them, which is what I call, this is basically would fall into the category of assume a rule. I'm not really assuming a rule. I'm assuming what a Greek letter means.
And when you say struggling list, you mean list of things to try when you find yourself struggling.
Right,
yeah.
Correct. Correct. These are what you should do once you've realized you don't actually know what you're doing. And the number two thing on the list is assume a rule, which is what this is. And I will say to them, you know, the reason people don't do it is because they're afraid that maybe their assumption is incorrect, which I say,
right.
That's not a fear. That's a certainty. Like assumption's going to be wrong sometimes, and then you're going to miss it. So what? The alternative, I don't know, is always wrong.
That's the key. The alternative is always wrong. If I don't have any idea what this is, I can't move forward and I'm guaranteed not to get it. Whereas if I roll the dice and I have a 30% chance of being right, then I have a 30% chance of being right, and that's better than zero.
Right.
I cannot tell you how many SAT and ACT students I've coached painstakingly to understand the difference between this word or formula or whatever means one of these two things and I don't know, versus it means one of these two things. Assume the first and solve it, then assume the second and solve it, and then look at your two answers and pick. Because oftentimes one of those two potential assumptions is going to turn out to be impossible to follow through to an answer anyway. And then you know what the word means. Then you know what the formula means. And in this case, now you know what the symbol means. Okay, so you've already gone back to working. Let's continue on here. I'll just mention that once I got through the whole pi as product thing and thought about this a little more deeply, I was able to come to the same conclusion that Michael, you mentioned, which is, okay, 2010 is a 2, a 3, a 5, and a 67. One of these four numbers is going to be the bottleneck here. And my thinking was, it's got to be the 2 or the 67. But wouldn't it be interesting if it isn't? Like, wouldn't that be a kick in the teeth if it's actually the 3 or the 5? Because I don't know. Like, the one thing about this that makes it interesting is largest power of the largest prime. And it's like, well, okay, 2 is going to show up a lot more than all the others. But whenever 2 shows up with another prime, the other prime is the one that's going to get counted. 67 isn't going to show up very much. Maybe 5 is the bottleneck here because it's the one. And then it was like, I don't know.
Well, yeah, that can't make sense though. Right.
Really? Because I couldn't make any sense. I couldn't get an intuition for what it should be.
Well,
So,
I
I don't know if are we trying to solve it out loud together right now or not? Or
I don't know. What do you? I tell you what. Let's get super meta.
I'll talk to you up to. Oh, go ahead. I'm sorry.
Let's get super meta.
Mm-hmm.
What would be most helpful for the people watching this? For us to take a moment to solve it together, or for us to kind of go back to our corners and then discuss what we thought about?
Because I have an answer. I don't know if it's right. I'm far from saying this is the answer, but I've just generated an answer based on what you guys said. Something I'm like, oh, duh.
All right, I propose we solve it together then. I'd like to hear what you have to say, and I'd like to see how it matches.
I would like to, I mean, in theory, if I had time, I would do a lot more work to find out if I'm actually right. Meaning I have an insight that leads to one of the
let's start with an assumption.
I have an insight that leads to an answer choice, which basically is when you said 2 doesn't come up.
It leads to an answer choice right off the. All right, let's hear it.
I'm just saying it doesn't mean, but I'm far from thinking I'm right, which is basically you're like 2 doesn't come up very much, and of course 2 is only going to come up when it is specifically a power of 2, and it's only going to come up. So therefore, only on the powers of 2, the biggest power of 2 less than 5,300 is 2 to the 12th, which means it's going to be the sum of the numbers from 1 to 12, which is 78.
Oh, now that's nice, right? It's like if it's 2, then an answer choice is here.
Right. Like it's not just a number; it's one of those 5 numbers. So I'm like, that sounds pretty. And this is very Pete, in that that's clearly not. That's very much not a proof. But it's got a good I would say I'm 80% likely I'm right.
I think it would. So I think we can say with high confidence that that's not coincidence.
Right.
Your worst case scenario is either it's a trap, which would be an extremely clever one, or
a really fortunate one as well, because you have
or you're subject to like an edge case error, an off by 1 error. There's this other thing you didn't think about error, that kind of thing. But like, bottom line is, I would bet my $100 in this moment that either it's E, or recognizing that E is very attractive is at the very least the first part of solving this problem, and probably a very big part of it.
And I will note that maybe they have very cleverly designed everything, but those 5 numbers being consecutive integers, like if the 5 answer choices were 6, 14, 38, 78, and 212, I would have more doubt about it. But it's very tough to arrange a problem like this such that the answer is one of the other 4 numbers that is immediately next to 78.
For sure. And that's why I'm saying that an off by 1 error is if you're wrong, that's the most likely way in which you're wrong. Because immediately that's how I'm thinking, right? It's like, okay, how likely is this to be?
It's not that hard, though. I'll tell you why. Because the first thought I had was just to take the number of multiples of 67 below 5,300, which is 79. So and there's a couple of reasons.
There's
a couple of reasons that doesn't work.
It's 79. That's horrifying.
They should have made 79 an answer. Would have fallen for it, because that takes about 5 seconds to do. So and if
Can we pause here? Can we pause here? Can we pause here and just have some shared props for the person who wrote this question? Because come on, that's pretty good, right?
That's pretty good.
That's pretty good. That is pretty good.
So but the fact that 79 wasn't there, and so and as you suggested about 2, like, well, maybe I'm double counting something. Maybe there's something here that's 67 times something. It didn't make any sense. I couldn't think of a way to toss 1 or 2 or 5 of the 67s out. So that's where we came in before, when I said, wait a minute, let's go to the other end, because I didn't have the same insight Pete had immediately about the summing. Yeah. So, yeah.
Okay.
Anyway.
All right. So now,
but I'll tell you, if 79 had been an answer there, I would have
jumped right on it.
I would have jumped on it, and I would have thought, well, I got number 25 correct in like 5 seconds. How smart am I?
Did you say that 67 times 79 is less than 5,300?
No, it's just over.
Oh, I'm sorry. Is that right?
Well, no, 67 to 79 will be just under. You're right, because 67 times 8 is 5360. So So it's going to be 5293.
So you're saying 79 would be right. In other words, you've neglected 67 squared, and the right answer is 80.
Oh, look at that. Yeah.
It's a good problem, right?
Yeah. They should have started this at 76 instead by my lights,
Yep. I'm with you. I'll just wait till you get into it. There's more. So why don't we take a couple minutes and let's dig into it. And for anyone who's watching, I invite you to pause and kind of ponder this out. While these guys are thinking, I'll make it a little harder for them and easier for you by just sort of spelling out some of the stuff that's going on here. And you can mute me if you don't want to hear this. So to spell out some of the things that are probably on Pete's paper, pow of 2 is 2, pow of 3 is 3, pow of 4, 2 squared, is 2 squared. Pow of 5 is 5, pow of 6 is 3, pow of 7 is 7, pow of 8 is 8, pow of 9 is 9, pow of 10 is 5, pow of 11 is 11, pow of 12 is 3. Let's skip ahead. Pow of 67 is 67. Pow of 2 times 67 is 2 times 67. Wait, no. 67. Pow of 2 times 67 is 67. Yeah, you're right. Pow of 67 squared is 67 squared. You guys have already said that 67 times 79 is just under 5,300, which means there should be 80 67s in there. And you've said that 2 to the 12th is 4096. 55, 60, and there are 78. So yeah, there are 78 twos in that product. We have done the 3s and the 5s. The 3s and the 5s can't possibly be it, can they?
Oh,
and
no. No, I got it.
You got it.
I got it.
So,
yeah.
All right. Let's hear it.
All right. So I thought 79. You point out it should be 80. I heard what Pete said, was persuaded by it. It's still niggling at me, though, that it should just be the 67 because it's the biggest one in there. When I thought it was 79, I wanted to take some numbers off. The conceptual problem I was having is there are prime factors of pow n that are well, specifically, are prime factors of 5,300 that are greater than. I'm not putting that right. Sorry, no, they're prime factors of pow n that are greater than 67. And at first, I thought those were just irrelevant, or would have the.
So what you're saying is, while pow of 2 times 67 is 67, and pow of 3 times 67 is 67. Pow of 71 times 67 isn't 67.
Right.
It's 71.
Right.
Ooh, cool.
And so, but I have to confess, I'm not quite sure. I think the way to go from there.
There aren't many primes above 67. All there is 71.
There aren't, but if you forget to look for them, you're screwed.
Right, we don't need many though, right? Because we just need one to get down into this one.
We need to get down from 80.
Well, hold on.
The only one is 71.
No, it's not.
No. Wait, between 67 and 79? 79, I guess, also. 79 also.
71, 79, and 73, Pete.
Yeah.
Oh, yeah. Good point.
Yeah. So then I'm going to say 79 minus 3 is 76.
Well, you should have said 80 minus 3 is 77.
Oh,
then I'm pretty sure you'd be right.
God damn it. Yeah. Oh, sorry, I shouldn't swear. Yeah. Okay. Boy, I like that, though. I mean, there are I talk to students about this with the SATs sometimes when it's not nearly as tricky, but sometimes there's a little trick and a big trick. And I once saw my brother-in-law jump over a hurdle and then trip over a chain that was like 2 inches off the ground. And that's kind of what I. So that's what I
did the hard thing but missed the easy thing. You're saying,
because he didn't know the easy thing was there, right? He didn't. He just and so that's what would have happened to me here. I would have been patting myself on the back for getting rid of those primes and neglecting 67 times 67.
Right. Right. I want to. I'm looking for another problem here, and I simultaneously want to invite the conversation of, okay, what in this problem should the viewer be taking away, or should you be taking away, about how you think, about how you could think better, about the nature of this test, about how the nature of this test interacts with human psychology, about high performance in a high pressure situation, about, like, there's a lot of different ways we can spin this. And I think we ought to be talking about them because we have over a century of combined insight into these issues, or at least trying to figure out the insights. And I want to surface those.
I was asking that same question for myself, because if I think about the worst thing I did, like the thing that would have led me to the wrong answer, as opposed to slowed me down the way to the right answer, was neglecting 67 squared. So I'd like to be able to characterize that as a sort of a broadly useful a way as possible, right? Okay. And so far, I don't have a broadly useful way to think about it. So far, the way I'm thinking about it is, don't forget the powers of the numbers when you have exactly this kind of problem. You know what I mean? So I would like to know if there's a way to characterize the mistake I made and a corresponding heuristic to avoid making mistakes of that sort.
Well, I have one off the top of my head. Pete, maybe you do too.
Well, I was just going to say, there's I don't want to get away from Michael's question, but there's an important thing with students, which is students will often try to take the lesson that is extremely specific to that problem away from it.
Oh, yeah.
As opposed to the lesson that you can more generalize. And that's a big thing just for the students. It's like your lesson, you want your lesson to be, because we're all assuming, let's find the generalizable heuristic, and the students are often not doing that.
Right.
They're saying, well, let's see, the next time I have a question that involves powers of primes and a huge product, and it's like, no.
Right. Correct.
So here's what I would take away from that as a starting point. Don't believe everything you think.
Okay.
And I say that with the idea that at the same time, we are trying very hard to think as many different things as we can, right? We're trying to think all these things. And there's this natural tension between, I need to come up with ideas. I need to brainstorm things I can do. But when I find one that's promising, there needs to be sort of a confirmation step before I lock it into my solution path. So when I say don't believe everything you think, I don't mean discount your own thinking. I mean, think many things. And when it comes time to plug it into a solution process, vet it first for a moment, then plug it in.
So just flesh out the vetting part a bit. Like, does that mean, I'm really serious.
That's a good question. Yeah.
Yeah. Does that mean it sounds vaguely plausible, or I see the mathematical underpinning to this? What does vet it mean from your point of view?
Well, I think what it means is that there's, in turn, there's a second level tension between the desire to extend thinking as far as you can, but not to extend it into falsehood. So, for example, Euler's approximate. Oh God, I'm going to get into like super technical, whatever. Okay, I've got some curve. I'm going to explain Euler approximation, right? I've got some curve. I'm an ant standing on the curve. I'm trying to figure out where I'm going to be after I've taken 1,000 more steps. One way to do it is face in the direction that I'm facing along the path and look at the point that's 1,000 steps ahead of me. That's going to be a decent approximation of where I'm going to be in 1,000 steps. Even though the road curves, 1,000 steps for an ant isn't that far. So the road's not going to curve that much, right? In the same way, Pow of 67 is 67. Pow of 2 times 67 is 67. Pow of 3 times 67 is 67. And there's 79 of those. Great. Okay. I'm the ant. I've projected forward 79 steps. Pow of this product is going to be 79. And yet, as the ant, I'm following some curves. So the next thought that needs to happen is, why is this wrong? How can this be wrong? Okay. Like Pow of 5 times 67 is going to be just as 67 as Pow of 3 times 67.
Yeah.
But Pow of 67 squared isn't. Now, how I thought of that, I'm not sure I can unpack, except to think that, like, it's the next natural thing to look at if you're looking at multiples. You know what I mean?
I'll unpack it a bit, which is what you're doing is you're looking at boundary cases.
Right. Edge
That's
cases,
basically
boundary
what
cases.
you're doing.
That's right. Yep.
And so I don't think it's just, I mean, there's a certain level where this is, sort of there's art to it, but some of it is these things that we've just gotten very comfortable doing, which is think of the edge case,
right.
think of the boundary.
That's exactly right. And part of the art is psychology, right? And you've built into your psychology the idea of, okay, if I want to look at a thing, then I've got to look at the edge. I've got to look at what that last step will look like. Mm-hmm. And that it doesn't guarantee that every step in the process will be right, but we both know that if it's wrong, the boundary is one of the most likely places where it will be wrong. Mm-hmm. So if your goal is to efficiently check something, that's a sensible place to start.
And if you had started, I think the natural edge case to test first is the very edge, right? You say, well, what's going to happen at 67 times 79?
Right.
I'm not going to count that one. What's going to happen at, although that took me a second just to be sure about that. And what's going to happen at 67 times 78? And you're just, well, that doesn't come up, sorry. But you back off, and you might, pat yourself on the back at that point and not even get to not see that 67 times 6. I mean, if you think about it, there's this 3 kinds of numbers, right, that we're looking at. Well, 4 really. There's 67. There's 67 times other products of other primes less than 67. There's 67 times 67 itself, and there's 67 times larger primes. And
I didn't think at first about how larger was an important thing too, but go on. Once I thought about 67 squared, it primed me to think about stuff on the other side of the square, but go on.
Yeah. Well, that's pretty much it. If you recognize that.
Primed, by the way.
Oh.
Well, it primed me. I didn't even. I should totally have taken credit with the straight face, but I didn't think of it. Well done. Yeah.
So the
opportunity lost.
Yeah. My friend Alex Gooderman and I were talking to a student from Hong Kong who was ethnically Chinese, but had a very upper crust received pronunciation accent. Mm-hmm. And as she walked out, I said, I found her accent kind of disorienting, and I didn't mean it as a pun. But Alex thought it was such a good pun that I decided I should probably go ahead and take credit for that.
Oh my gosh.
I'm just going to roll with this. Yeah.
Horrifying.
It is horrifying. Yeah. But I mean, it's like there are lots of problems but because they're more familiar, where you'll tell people there are 5 numbers you care about, right? Or sort of. There's like or 3 numbers. And then the 4 ranges they give you. There's -1, 0, and 1, and then everything falls around those. Nothing that does only right. And so this is that's so familiar. This is a similar kind of logic, but less familiar to me. So when you said you start with when you said 2 times 67 is the same case as 67, the same case as 3 times 67. If you had framed it that way for me, I would have immediately gone to say, oh, the next one that's relevantly different is 67 times 67.
And I'm saying, therefore, you should frame it for yourself that way when you begin a list like that. And that's inculcating that habit of thought is not hard, but it's subtle. And so most people never even consider doing it. Mm-hmm. Okay, so before I show the next problem, I have to share this. Speaking of your disorientation pun. So 15 years ago, my friend Sean Barrett, who is just a genius, said, he gave me this Tom Swifty. I'll worship any god that helps me steal other people's trousers, Tom Swifty said pantheistically. Sorry.
Oh, no, I was going to see if I get it. Yeah, okay.
Sorry.
Nice. Very nice.
Pantheistically, heistically. Yeah. Oh my God, so good. So good. Yeah, right? Come on, I have a shirt that says "Dad jokes are how I roll." I roll, EYE, roll, because that's my thing, baby. Oh yeah.
Let me tell you. I have a Tom Swifty that I came up with.
All right.
Yeah, it's how do you do it? Apiaries are my favorite subject for painting. Tom said, Bemusedly.
Bemusedly.
Yeah.
I like it.
Yeah.
That's really, bemusedly.
Yeah.
That's
Okay,
some good stuff, people.
Here we go.
Come on. I'm not going to make any such strong guarantees about the loveliness of this. It's a lovely problem, but this might be a little bit more involved. We'll see.
How many squares of sides?
God.
At least 6. Huh. I don't know. It looks so easy.
How hard can it be?
No, that's very, very, very hard because it looks so easy.
Oh, right. Yeah, for sure.
Yeah.
For sure.
Okay.
Well, I know. I will say, I know not. I'll say the very first thing I did is I looked at the choices. Like, I can't enumerate this. Like, literally, that's the first thing I did.
Yeah.
Like,
all right. Yeah.
So,
but you can draw a couple of cases. I mean,
Sure. I'm just saying, like, that's in terms of process. That was the very first thing I did.
Mm-hmm. Yeah.
Oh, yeah, this is good. I forgot about this one. For anyone following along at home, this is, I don't remember which one this is from, but it's from somewhere around 2010. Let's see. This is the 2009 AMC 12B. And in case it isn't clear to anyone following along, I'm not claiming that these problems are necessarily representative of a modern AMC 12. I mean, they're pretty close, right? But we all know that the AMC has shifted in its tone over the last 3 to 5 years in a significant way that affects preparation. But the kinds of skills that we're demonstrating here broadly apply to AMCs throughout its history, particularly the last few years, as well as Amy's, both ancient and modern. I'm still waiting for the bag of sand to hit you guys in the head.
Well, I don't know. I mean, my answer is not one of these options, so I've clearly done something wrong.
Well,
if I had a
is that so
second...
clearly? Let's hear it. Okay. Let's hear it.
All right. Can I mark on here?
I don't know. I doubt it, but try.
Oh, okay. Well,
I give you permission.
Yeah, there you go.
I don't think it's going to do anything, but
I'm going to click on the gear up here and see if that does.
Yeah.
No.
I do have. This is my mouse pointer, so I can move it around in response to what you say. But that's the best we have.
No. All right. So you have 4 possibilities here. I don't know why I said 4. You have 6 possibilities here. You have squares of side 1, side 2, side 3, side 4, side 5, or side 6. Oh.
No.
So how many squares of least? Oh!
Okay, let me just say, by the way,
I didn't read it correctly.
First of all, were you doing of at most size 6?
Yes.
Okay,
now it's completely different.
That I'm just going to give an answer that I completely cannot prove.
Sure.
But based on, just a problem solving thing, which is this problem is completely symmetrical. Everything about this problem is symmetrical. So I see no reason why it's going to be, it seems like the answer should be a perfect square. So I would simply guess E at this point, because this is
a perfect square. It should be a multiple of 4. Yeah.
But it's not anyway, because there's
it should
the
be,
one in the middle.
Wait, hold on. This is gold.
No.
Why should it be a perfect square instead of a multiple of 4?
By that reasoning, it should be 4 times a perfect square, the plus 1.
Wait a minute.
Missing something about
what are you guys talking about?
Maybe I'm missing something about the problem.
Okay,
or maybe we are, Pete. But you got to spell out for us why it should be a perfect square.
And this is where I get in trouble because because
we're on the edge of our ability here. Let's hear it.
Okay, just basically because it's going to be the same through each, and this isn't going to make logical sense. I'm aware of that.
Just that's all right.
Okay, because it's going to, however many starting points you have, from any quadrant, it should be the same throughout. I'm not going to be able to prove this. That doesn't. I mean, that's like.
I love that you have this intuition.
No, but
the best part is
I'm not done with this problem, and as I've started it, it doesn't seem to be. That doesn't seem to be right because I've started it by saying how many points could I, how many I mean, so I'm not done with this problem based on my work. What I just said
No, I
is
got it.
right.
But I love the idea that you're thinking things and then you're not believing what you think. Like, that's exactly the game. It's like, this should be a perfect square. Or not. Like, fine. Like, whatever. Great.
Like if you said you have 5 seconds left on the test, guess something, I'd have to think about the guessing penalty on an AMC or whatever.
This is super important. People get to that, oh my God, I only have 5 seconds left mindset way too early on this test.
Yeah.
Way too early. Like, and the thing is, when you're thinking about a problem like this, you can go through an incredibly convoluted chain of insights or logic or whatever in what feels like it must have been 2.5 minutes, when in fact it takes 3 seconds, because that's what happens in brains sometimes.
I just realized what I was doing before was woefully incomplete.
Can you explain to us where it came from so that we can benefit, even though
the thing I was thinking of, which is correct, but and I was getting an answer that's way too small, so clearly it was incomplete, was, okay, if I start at the top left corner, if I start at -7, I can draw a square. I can go across to 4 different points and then draw a square going down. I can go to, if I go over a distance of 6, I can go to -7. Oh crap! I missed something about the problem. Okay, actually, wait. There's going to be more. Okay, actually, I have to redo this because I didn't realize that we were skipping the numbers between 1 and 2. I just had it. Oh, I have to redo this. I actually did what I did might work. Actually, I didn't. I missed something on the problem.
So in other words, you've counted some squares that have coordinates that are off the lattice, that are, for example, 0,7 or something.
There are also going to be a lot more because yes, that is true, but also because basically I assumed that once you were down to the 4th row, there was only 1 left because I was looking at consecutive integers. I was saying that for the first row, I just counted out like one. There are going to be 4 squares. For the second row, there are going to be 3 squares, as if they were all consecutive integers, which they are not. So actually, that means there are going to be more than I had previously thought. The other thing I have to think about, which I'm literally in the, hey, what about this, is squares that are basically perpendicular. Like, there was no rule that they have to be nice, easy, squares that are like,
That's the bag of sand that I was talking about earlier. How long will it take you guys to realize that the square can be tilted? Right. But apparently that wasn't
No, I was doing it, and I was like, there are 2. I discovered one problem. The other problem is this doesn't have to be the nice little square I want it to be.
Welcome to AMC 12 problem 25, man. Yeah. It's like, oh yeah, they can shiv you, but good.
So that's where I am with this right now.
Yeah.
And I just restarted as soon as Pete started talking because I had misread the question. And by the way, had the wrong answer to the question that I was thinking about anyway, because I had not considered sort of off-kilter squares. So here we go.
So are we going at? Are we problem solving now?
Are we going back to the problem, or?
I think we're gonna solve, but I have the feeling we're gonna solve this out loud. Okay. And maybe
one should start with what I'll call the easy squares, and then deal with the what about weird diagonal things.
I had a lot of problem with the easy squares, honestly. Like, it took me a while to figure out what the heck is even going on here. And I finally, I was like, how can I count these? And I finally came to the conclusion that you just articulated, which is, let's start by picking the upper left-hand corner of the square and going from there. Mm-hmm. And then there are 25 different upper left-hand corners we can have. And for each of those, there are, in some cases...
Did I cut out, or did...
No, there are, in all cases, multiple ways to complete the square from there. In fact, I think there's 5 for each. I think that's right. I think for every point you choose in quadrant 2, there are 5 squares you can make made of vertical and horizontal lines. Right. Because you can go across to any of the 5 points in quadrant 1, right. And that uniquely defines a square, which means the answer 125 would be right if we weren't allowed to have tilty squares. And now I feel like I'm on the right track because I have found a minor trap. And I trust that Michael will be back someday.
And now I have to think about tilting things, and this is
well. And the problem I have here is if you start with negative 7,7, there are no tilty squares because it'd be off the lattice.
I hadn't even gotten that far, but that makes sense.
Whereas I can find other points where it's like, oh yeah, I can totally tilt that. And it's like, oh God, what governs how tilty it can be?
Well, it needs to be at least a distance of 4, a distance of 6. So I would start thinking of what that means across and down. So like, for instance, 5 across and 4 up and down is root 41. That's going to be enough.
I'm not sure that figuring out that distance is the important bit. Like I'm thinking in terms of like negative 6,7. If that's the upper left-hand corner, then I'm one step to the right of negative 7,7. Yeah, go ahead.
No, I was going to say that one thing I just realized is that it does not have to be true. Well, no, it is integer coordinates. All four vertices of the square must be these integers. It can't be that it's some other point within this lattice, but not one of these points. They must
right.
all be lattice points.
Right. So I'm seeing that like negative 6,7 is one step to the right. All right. So I'll use my crosshairs. This point is one step to the right of this point, which means that if you go one step down from this point and one step to the left from this point and one step up from this point, you will have defined a square.
How cool is that?
And it's like, okay, so I could do 2 steps over, 2 steps down, 2 steps over, 2 steps up, or 3 or whatever. And then it's like, okay, what if I start here? Well, if I start here, then I can go 1 step over and do that whole business. I could also go 1 step to the left, but I think the way I want to think about this is starting here, I only move to the right or down so that when I get to this point, I'm only moving to the right or down. Otherwise, I'm going to double count.
There's an important point you're getting at there, which people get messed up when they're doing sort of enumeration type things, which is you want to count in a logical manner, meaning you want to count in a systematic manner, because oftentimes the students will just think of the next one that comes to them, and then they're stuck because you don't know whether you've either undercounted or overcounted or what have you.
Whenever you're going to count or list things, you need to count in order or you need to list in order. And then the sensible question is, well, in what order? To which my answer is, I don't care, pick one, but be consistent.
But when
that's something you're just intuitively doing that. But so does that mean it's going to be?
Well, there's a way to characterize that a lot of times, which is some sort of lexical order, right?
Alphabetize them
or whatever. Yeah. So
yeah.
Now I missed almost everything you guys said. I probably had disappeared from your screens, so so I'm no doubt doing something less efficient than what you were describing.
Well, I have determined that the answer to this problem is 145. So done with that. Crap.
So the question is,
but that wouldn't be bad if you had determined that.
There are 120. One way to look at it is, okay, for a given point, what is the maximum number of squares you could have? Like which point, where's is the maximum 1? Is it more than 1? Other than the basic square, other than the basic squares. Which
I can make more than one rotated square from -5, 5.
That's kind of what I figured. So I would look at the types of things and how many points there are. So like what you're saying is.
I think I just lied. I think I'm wrong about that. Wait a minute.
Because
I think I wanted to say -6, well, I tell you what, I can make
okay, so I'm going to try to categorize this. So basically, -7,7 we said had 0.
-7 has 0, and so what we're counting now is rotated squares that are not aligned with the axes.
125 that we got. So then, because basically, look, -6,7 just about has to have the same answer as -7,6. Whatever number that is.
I claim it's 1 for each of them, which is where I get 145.
Right. But okay, so now we have to look at other ones. Like, okay, what if you're 2 away? What if you're at -5,7? What's happening?
You know what I did? Do you know what I did?
I do not.
I am absolutely correct that there are exactly 20 rotated squares if you only count squares that have the origin at their center. I'll tell you what, here's my lemma. My lemma is any lattice point not on y equals negative x has exactly one rotated square associated with it with the origin at its center. Because every point that's on y equals negative x can't be part of a rotated square because reasons. Can't be part of a rotated square with the origin at its center because if the origin's at its... I've got it. Okay. Pick any point you like in the second quadrant. Generate the square that... okay. Pick any point you like in the second quadrant. Draw the segment that goes from that point to the origin. Okay? Take that as a vector or a line segment, rotate it 90 degrees subsequently 3 times. And that line segment will describe the other 3 vertices of a square guaranteed. The only issue is that if you start with one of the lines on y equals negative x, you will, by definition, be defining a square that isn't rotated. Whereas in any of the other 20 points, it will be a rotated square.
Okay, that makes sense. It just
the problem is that there are other squares. For example, consider how can we do this? Consider negative 7, 6. I've been thinking about this as... Okay, so now what I think we want to do is we want to draw the segment that goes from there to negative 1, 1 and rotate that guy around. And I think what we're going to find is that the resulting rotations all land on the lattice, just not symmetrically because its center is negative 1, 1, not 0, 0. I'm sorry, I have no confidence that this is a sensible way to go about this. I'm in the stage of coming up with a thing to think. I have not yet decided whether I should be believing what I'm thinking. I'm just saying, oh, thank goodness, a ray of light. I wonder if that leads to a trap.
It seems to me... I'm sorry, go ahead, Michael.
Well, again, I'm probably repeating something that you said before because I was out of the room for a while, but I just want to be clear. Are you assuming that... when I draw a side of a square connecting 2 of these points, that I will be, because these are all integers, right? That this will be a 3, 4, 5 with 6, 8, 10, 5, 12, 13, 9, 12, 15 square. Am I?
Certainly not.
Actually, a little bit more than that. I'm sorry, but let's see.
No, these are not going to be Pythagorean triples.
Oh, right, because those aren't squares anyway. But
it seems to me
that the side. What I mean to say, of course, is not that that's a square, but that the hypotenuse of such a triple will be the... Yeah, but of course that doesn't have to be the case. Because all I need is for the hypotenuse to be an integer. Those will be included, but all I need is for the hypotenuse to be an integer. I don't need for the...
You don't need the hypotenuse to be an integer. You just need it to be the same for all 4 sides, which symmetry does for you. So, for example, let's think about this the square that goes negative 7, 6 and 6, 7. Like that's whatever that is, right?
Yeah. You're right.
Square root of 170 or whatever it is. I don't know.
Yeah. I was making too much of those
I'm not good
integer points.
At the visualizing part of executing, it seems to me the right plan is to classify the types of points you have, so you can basically like I just cannot possibly see, even with my poor skills, that negative 7, 6 and negative 6, 7 have to be the same as each other. Like with the symmetry of the problem.
You can't see that this upper left corner and this upper left corner...
They have to be the same. I'm saying they must be the same.
I agree that however many squares you can build out of this is how many squares you can build out of this.
That's all I was saying.
I agree with that 100%. And I guess another point that you're making is that all we really need, we don't need to consider all 25 of these upper left-hand corners.
Right.
We just need to consider 15 of them and possibly only 10 because we might not need the ones on the diagonal.
Right. We need to look at some of those cases and start working it out from there. Correct. That's all. And I'm going to get lost on the actually figuring out how many there are for any particular point because that's not my forte, but I would give that a shot.
Yeah.
But that seems like the right process.
Let me point something out. One of the ways in which I made a rotated square originally is I considered the largest possible square that had this as its upper left-hand corner and this as its lower right-hand corner. And then I said, move down a step or left a step or up a step or right a step from there, and you'll get a rotated square. I'm now considering that if you try to do the same thing with this as the upper left-hand corner and this as the lower right-hand corner, that it will fail because, nope, that won't fail. That will work. Because there is a point, one to the right of this, one to the down of this, one to the left of this, and one to the up of this. So I want to point out that Pete and I are advocating for different paths through this problem. And I don't have a value judgment on which is better, but I'm noticing that we're getting into sometimes a trap that I often get into on my own, which is, I see two different paths. Which one should I take? Like Buridan's donkey, right? Oh, there's a good idea there and there's a good idea there. Maybe I should stand here in the middle. It's like, no, flip a coin if you have to, pick one and go, right? If you're super expert, take a moment to think about what's going to make more sense. And I think Pete and I are each going to follow our own individual plans, not because mine is better than his or vice versa, but because mine makes more sense to me because that's
mine. I'm no way claiming mine is right. Mine is mine.
Well, and it's not yours because you're a genius. It's yours because it fits the contours of your mind best.
Yeah.
Yeah. Wait, I still have to work this out? That sounds like work. I had it and then I lost it. I'm going to try it again.
I have a theory. No, this is why I have something that basically one of the things I do when I'm problem solving is I basically invent solutions, which I absolutely cannot prove, and then see if I get an answer choice. So I did something that generated an answer choice.
All right. Give me a minute because I think I'm in the middle of doing the same kind of thing. It's going to take me an extra minute and I'll explain it afterwards, but I have a new answer that's bigger than 145. I just don't know if it's one of these answer choices. I've got to count it out. Let's see now. How did I do this? I've got
Oh, that's wrong. Okay, the thing I just said is wrong. Forget it.
Okay.
Oops.
God, I'm so close, but
I do want to bring up a test taking point before you come up with your grand awesome solution.
Go ahead. Do it up.
Oh, so I clearly do not have the right answer.
Okay.
I think I know where I'm lacking, but I do want to make a test taking point, which is my answer is 180, which self-evidently is not the right answer. But my point is, if I were now having 5 seconds left, I would guess C. A lot of times people are like 180 is wrong. I mean, it is wrong, clear. But the odds that I'm off, like on the previous case where if Michael wasn't counting a couple of duplications and everything, so he was off by a couple, strikes me that instead of being 20% likely to be right, I would say 175 is at this point from where I'm sitting 35% likely to be right instead of 20.
And 35% is okay. Yeah. Similarly, if there were an answer choice that were 90, that might also be really compelling.
Sure.
Because you might be double counting.
Sure.
This is very different from picking the number that is closest to your answer. That's a terrible strategy. But that's not what you're advocating for here. So let's distinguish between those. I believe the answer is 180, and so I'm going to pick 175 because it's closest is BS. I think the answer is 180, and I'm going to pick 175 because it's plausible to me that I could have miscounted by a little is gold. And there's a subtle difference there, but it's important. Would you quibble with anything that I've said there? Or maybe just out and out disagree?
No, in between. As a teaching thing, you're being more nuanced than I am. I when I am teaching, really am big on simple heuristics. So I just tell them, I mean, basically, yeah. I tell them to guess what is closest. What you said is clearly more right than what I tell my students. I mean, there's no question.
But I think you're making a really important point, and this gets into a conversation Michael and I have had on the side, right? There's a point at which getting into the more accurate heuristics doesn't serve the student well because they can't assimilate that information.
Oh, it is one of the most common things I've seen. I mean, you see it more when you teach something like an LSAT, a more complicated test, that like people start getting into all this stuff. You need really simple decision trees. I remember when I was tutoring the SAT originally in the Mesozoic era, the test was extremely time pressured, and you'd have tutors saying like, skip this one here, then do these three, come back and do this. And it was logically correct. And I was like, we are not doing that. Like, we are absolutely not doing this, because way too much of the energy is getting put into following the pattern as opposed to doing problems. And so you have, part of the tutor's job is to find the right balance between what is most technically correct and what is simple enough to be implementable and leaving brain energy for doing other things.
Well, I think there are two comments about heuristics that strike me here. One is, if I arrived at 180, which I have not, the question I would be asking myself is it possible, or is it more likely that I neglected this large class of 20 squares, or is it more likely that I double counted?
Oh, that's 5? That's a really good point.
Yes, it is.
And of course, I might not be double counting.
By the way, that's actually a point, because I would assume I've undercounted. I would assume, given what I've done here, I'm much more likely to have undercounted than overcounted. That's a really good point.
Plus, your error is much more likely to be a multiple of 4 than not.
Yeah, that's good. The other thing,
and that means if I get 180, I'm picking 200 and moving on.
Yeah, no, it seems that's a really good point.
Speaking of kind of avoiding complexity even when accurate, I wonder if this has occurred to you, Pete. Sometimes you'll ask students with a 5-answer multiple choice question. You'll say, just pick it's going to be a lot easier to back solve, right? So just try try one of the answers out. And of course, there are these circumstances such that you can tell when an answer is too big or too small, right? Like if it's a question about factors, you're not going to do that, right? But for lots of other questions, you can say, well, they must have more than 7 cows then, right? Because this is way too much feed per cow, or whatever it is. And and if you leave out that some numbers are easier to check than others, so I might check 2 and 4 before I check 3 and a third, because it might take me less time to determine 2 is too small and 4 is too great. But it occurred to me, and I didn't tell my students to do this, but if all 5 are equally easy to check, it actually, and they're in ascending order, it's actually more efficient to start with B or D than it is to start with C. You'll have
because if B is too big, you know what the answer is?
Yeah. Because if B's too big, you know what the answer is. Then you just check, and B's too small, you just check D, right?
And then you know what the answer is.
Then you know what the answer is, and it's almost no difference between choosing C to start with and choosing B or D to start with. But
almost no difference. Yeah, almost no difference is not no difference.
Yeah,
we'll take an advantage anywhere we can get it.
Yeah, except that it was one goddamn thing to think about for the student who.
Correct. I would actually, as a matter of coming up with a more efficient path, that is, I don't think I would want to teach, even though you're right. And I didn't teach it, in fact.
Start with C.
Yeah.
Yep. Okay. Let me tell you why the answer to 25 is E. Mm-hmm. Now, the reason I'm leading off with this is that I'm not sure that it's E, but I have a path that gets to E. And if it's wrong, you're going to sniff it out, I think.
Mm-hmm.
Okay. So let's go back to my earlier theory that said the correct answer is 145 based on the following observations. there are 125 of these squares that are not rectilinear, but aligned with the axes. Mm-hmm. And I claimed incorrectly that there were 20 that were skew. And the way I did it is I said, start with this point in the upper left and move 1 to 4 units in the skew direction, mm-hmm. which is either this or this, and then mirror that across all the others. So in other words, if I move 3 points to the right, I then move 3 points down, 3 points to the left, 3 points up, and now I have a skew square, which means there are 8 skew squares that are constructible by starting on this point and then skewing. 6 from this point, 4 from this point, and 2 from this point, and none from this point. Therefore, there are 20 skew squares. It's wrong, but there's some value in that. Because now what I'm going to say is, great, I'm going to count the skew squares again, only this time I'm going to do it in a 2-step process.
Direction. Okay.
Well, not a different direction. I'm going to do the same thing, except now, rather than assuming that its center is 0 and therefore the lower right-hand corner is 180 degrees rotated from the point, I'm going to correctly assume that from here, the lower right-hand corner can be here or here or here or here or here.
Ooh.
Then it should work. So I start with the original 8 points I have that assume this corner. Then I come up here and notice that only 6 skews will work because there are only 3 available points to rotate to in each direction from here. So now I have 8 plus 6 plus 4 plus 2 plus 0. That's 20. Wait, I thought it was 40. Hang on. Wait. 8 plus 6 plus 4 plus 2, 20. Instead of 8. And now I'm going to say that instead of my original 20 points, there are 20 times 28, 50 extra points. When I said the answer was E, I meant C. I now claim that there are 50 skew points based only on the observation that my original calculation was off in the case of this point by a factor of 2.5. And therefore my total is off by a total of 2.5. And therefore, when I counted 40 extra points, when I counted 20 extra points, I should have been counting 50 extra points. Now, I'm doing an Euler's approximation, right? I'm claiming where the ant is going to be after I've done the entire thing without really knowing if this holds water. But I feel like, okay, 175 is plausible. Now I have to go through the rest of the points and think through how this actually works.
So I don't know the answer, but I'd like to make a case against 165, about 175.
Ooh. I see a case against 175 too. Please go ahead.
And
now I know how to do it.
It seems to me that every answer, that every possible square, whether it's skewed or not, is almost everyone. Actually, now I'm not so sure. Is going to show up 4 times.
Sure.
Except for 2 squares that will not show up 4 times.
What 2 squares won't show up 4 times?
The largest possible square. Sure,
it will. We'll count it 4 times if we.
The square with sides of 14. You're going to count.
No, I know what you mean. Like upper left to lower right. Like
yeah.
What counting mechanism is only going to count that once instead of 4 times?
Forgive me. I mean, like after any correction, that there are.
Okay.
That's going to be So the any other square, and then so there's that one that's you're only going to count once, and then there's the one in the center that's. That has sides of 6, you're only going to count once. And I don't like where this is going at all. So never mind. So never mind. Because where it's going for me is that the answer should be 2 more than a multiple of 4, but only one answer matches that description. And I think you've already eliminated that answer.
150. Yeah.
Yeah.
Okay.
I don't know what's wrong with my reasoning, but if it leads to a false false answer, there's something wrong with my reasoning. I was trying to think of the off-skew ones, but I don't believe there's any. I mean, there can't be any.
I've got it.
Yeah.
Yeah. Here, check this out. It follows the pattern that I had before, except that I was doing it wrong. Okay, so here's the deal. This is going to wind up being, I think it's going to wind up being 150. No, I don't know what it's going to wind up being.
Okay.
All right. So from here, I continue to claim that there are 8 skew squares from this upper left and this lower right. I continue to claim that there are 6 from this upper left and this lower right. So 8, 6, 4, and 2, and 0 for a total of 20 skews from this point. From this point, I claim that there are 6 plus 6 plus 4 plus 2. Here's why. If this is the upper left-hand corner, there are 0 skews from here. There are 2 skews from here, here, and here. There are 4 skews from here, 6 skews from here, but still only 6 from here, because if this is the upper left-hand corner, we can't count all 8, because counting 8 would involve moving 4 away from this, which can't be done from here. It's capped at 6. So we've got 8 plus 6 plus 4 plus 2, 6 plus 6 plus 4 plus 2, 4 plus 4 plus 4 plus 2, and 2 plus 2 plus 2 plus 2.
Which is 60.
Which adds up to a number. Is that 60?
I believe so.
Oh, tell me you're kidding.
Numbers, I believe 8642 is 20. 6642 is going to be
18.
18. 4442 is going to be 14. And then 2222
is 8.
So yeah, it is 60.
Damn, that sounded so good in my head.
I can't pretend I was completely following that. I think I would need a picture.
I'd be happy to draw it, but like,
I got the general idea, which is that you can't fall into the gaps there, right?
Yeah. So it seems like, as I'm thinking ahead, right? If I pop open the solution here, here's what I think we're going to see. I think we're going to see that from any square there are certain invariants, or from any lattice point there are certain invariants, that we can do this combinatorically somehow without resorting to these weird cases. I think they're just going to say, well, we can clearly see that.
My assumption is that it'll be classes of points, meaning, the top left is 1 and the other 2 are symmetrical. And then I'm not quite smart enough to see, is -5, 7 the same as -6, 7? I'm not quite smart enough to figure that out, or good enough visually. But
that's how I tried to do it originally, was on the assumption that let's suppose you draw the line. X equals -y through here, right?
You know what? I'm going to put my $100 on D. I'm sorry. I just realized something else. Go on.
Yeah. Well, if you draw the line X equals -y through here, it seems to me that the points that the points that reflected one another would behave the same way. So in that way, you'd have you could start to get down to classes. But that's not actually true, by the way.
Well, here's my argument. Here's my argument in favor of D. It goes like this: we know that there are 125 that are horizontal vertical. I stand by my argument that there are 60 of the type that I just counted, and I note that those 60 all have centers along the line y equals -x or y equals x. I have failed to count the ones whose centers are neither at the origin or along either of those diagonals. For example, I see a square centered at 0, 1. And however many I didn't count, it's a multiple of 4.
That sounds good.
And so it's 240 more than my answer.
It's only 20 more than your answer, but that's okay. Wait, you got
20 more than my answer?
Your answer is
because I can arithmetic.
No. That's actually E then, because you're at 185 right now. Based on your work, you're at 185.
Oh, then it has to be E.
Yeah. Then it's got to be
then
E
it has to be
based
E.
on that. You're at 185 right now.
I can count. Great. All right, whatever. So then it's E. For God's sake.
Let's find out.
Really? We're going to find out? We're going to look at... All right, fine. So let's see here.
Yeah.
No. I mean, I guess it wouldn't make any sense to...
I'm well past contributing useful here, so...
all right, give me a second here. I'm going to look it up. Everyone here has probably already looked it up on their whatever, but I said it was the 2009... No, I don't have the solution to this one. No, I'm just kidding.
Interwebs, baby.
It is E. All right, hang on a second.
Yeah. I could open out a problem solving myself, I think. Yeah.
I mean, you could, right? But like,
let's wait for you. Yeah.
Let's do this in the most horrifying way we possibly can, which is start by looking at this answer here. Let G sub I be the subset of G contained in the ith quadrant. For a fixed I, the maximum distance among points in GI is blah, blah, blah. Also, okay, so once you're doing that, now let's look at the rest of this.
Yeah.
Holy cow.
It's like, are you kidding me? Holy my God. All right. So I think you're absolutely right that looking at AOPS is probably going to be a better
that was the AMC thing.
That was the official solution that year. Okay. Yeah. So I think looking at AOPS will probably make sense.
No, what you would want to do would be to go read through them and then see if you could distill from them some sort of.
That's the way it normally goes.
Yeah.
But I really like our process on this because it was so ugly, but like we had the right milestones in place the whole time. We bumped our shins against a lot of furniture and we found the exit. Like that's, I mean, it's like they say, first the enlightenment, then the laundry, right? No matter how expert you are, you still got to just do the steps. And sometimes it's ugly.
Fair enough. Yeah. I think you're sharing a lot of credit needlessly when you say we, but
I don't know. So I tell you what I'm going to propose. Let's stay on the line after I stop recording, just to debrief a little bit. But first of all, any sort of closing thoughts about either of these problems that we haven't had a chance to discuss earlier in this conversation?
Well, I think my main thought about the last one would be there are some problems that you should be doing with a pencil on the page.
Oh God, yes. I've done a very good job of illustrating how not to do it in that respect. You're 100% right.
Well, I mean, you were working with the constraints we've imposed on ourselves, so.
But I mean, I could have pulled out paper and been working on the side, and that would have saved a lot of trouble. And we all know it, for sure.
Yeah.
No, I think we did it was a fun little deep dive into those. I think I'm good for now.
Okay, sounds good. In that case, thank you both for joining. Please stay on the line, as I say, after I click this button, and I'll look forward to talking with you in the future, guys.
Great. Thanks, Wes.
Thank you.